We're going to talk about the multiplication rule of probability. So we're nearing the end of our rules of probability. So far we talked about the addition rule of probability. We talked about the conditional probability. We looked at joint and marginal probabilities in a contingency table. And now we're reaching the end of our rules of probability, this time the multiplication rule. Now, if we actually take a look at the formula for conditional probability, okay, we talked about conditional probability in section 4.5. Let me recall what that formula was for conditional probability. The formula we had for conditional probability was this one. We said probability of A given B is equal to probability of A and B divided by probability of B. Okay, and remember that what's after the bar here, the latter part, is what shows in the denominator also that event. Now if we cross multiply these two, we're going to get probability of A given B times probability of B is equal to probability of A and B. Now if you look at this, is precisely what this formula is, actually this one. There are two versions of this formula, but they really mean the same thing. But that's how the formula, which we call the general multiplication rule, is created. Okay, so the general multiplication property again tells us the joint probability of A and B is equal to the marginal probability of B times conditional probability of A given B. Now, of course, events don't care how we call them, which one is A, which one is B, so you can actually use the top version or the bottom version of this formula. But that's how the formula is created, and it's pretty simple. This formula allows us to do two things. One is to find the joint probability. Again, probability of A and B is what we call the joint probability of A and B. It allows us to find that, and also we use this in a way to test for statistical independence, and I'll show you that in just a moment. So when we talk about statistical independence, that means the occurrence or non-occurrence of the one event does not affect or influence the probability of occurrence or non-occurrence of the second event. If that's the case, then we call these two events independent. So probability that, let's say, somebody's going to call in sick at their job has nothing to do with whether, let's say, there is an accident on the road elsewhere in another city. So the events are totally unrelated, and in our case we call these statistically independent. Now, how do we ensure statistical independence in our experiments? It's done by the way we conduct the experiment. Okay. Now, I have also written this down here. Both of these are result of multiplication rule, and so we can actually, if the statistical independence does hold, that means the occurrence, non-occurrence of one does not affect the other one. That means probability of A given B should equal to probability of just A. The given part here, given B has occurred, bears no weight on probability of A. It really doesn't change it. And likewise, probability of B given A has not occurred has no influence on probability of B occurring. Therefore, that would be one way to test for independence also. Now let's take a look at this example that we have here. So in this example, let's say we have 4 green, 3 black, and 7 red marbles, and we're going to draw 2 marbles here. Number 1, we're going to draw it with replacement, and in number 2 without replacement. We want to know what is probability of a red marble on the first draw and probability of a black marble on the second one, ultimately. So I'm just breaking it into 3 problems for you. So first of all, probability of a red marble on the first, because there are 7 red and 14 total. So that probability is going to be 7 out of 14, 50-50, right? Now, because we are conducting the experiment with replacement, means we're going to put that marble back into the jar and then draw a second marble. So that red marble, presumably, is now back in the jar. So we have restored the jar back to having 14 marbles. So probability of black marble is going to be 3 out of 14. Now, for the joint probability that both of them, red on the first, black on the second, we're going to multiply those using independent events, and that probability of R and B is going to be probability of red on the first, black on the second. That's going to be 714 times 3, 14. Notice the denominator is restored to 14 for probability of a black marble. Now, in number 2, without replacement, well, the first draw is not going to alter, right? The probability of red is on the first draw is still 714. What's going to change now is because we're not putting that red marble back into the jar, therefore now there's only 13 marbles in the jar, 3 of which are black. So the same probability now is going to be 714 times 313, and that's going to be a different probability. Okay, so the probabilities actually are changed depending on how we conduct the experiment. Now, hopefully you follow that one. Let's try this other one together. In this next example, what we're doing is we are tossing a coin, fair coin, twice. Okay, now there are 2 possibilities because this is a fair coin. Okay, and with a fair coin, the possibilities are head or tail, right? So our sample space is going to be a head or a tail. Okay, and then probability of each of those is going to be 1/2. So in question number 1, what is probability of tail on the first toss? So that's probability of T1, means on the first toss. It's going to be 50-50. In number 2, tail on the second. Well, because these are independent, right? Tail on the second, still going to be 50-50. Now, what is probability of tail on the first and tail on the second? So that's question number 3. Probability of T1 and T2. Well, that's going to be probability of T1 times probability of T2 given T1. Now, probability of tail on the first was 1/2. And what is probability of tail on the second, provided we flipped and it was tail on the first? That's still going to be 1 out of 2 possibilities, so that probability is 1/4. Notice the conditional probability of T2 given T1 was exactly the same as probability of just T2. And this answers question number 4. Are events tail on the first, tail on the second independent? Well, it turns out that this is true. That's going to be 1/2 equal 1/2. So yes, they are independent. That's one way to verify it, or we can actually do it this way. We're going to say probability of tail on the first and tail on the second is going to be probability of tail on the first times probability of a tail on the second. Tail on first, tail on second, we found it in number 3 to be 1/4. And in fact, probability of tail and 1/2 probability of tail, that's just the marginal probability of tail on the second, 1/2. Again, this one is yes. So you can test for independence different ways. So hopefully you get the idea, to have a grasp of this conditional probability and the use of multiplication rule. Let's take a look at this one exercise that is in your book. In this exercise, the question reads, the National Center for Health Statistics compiles data on injuries and publishes the information in vital and health statistics. So a contingency table, remember a contingency table is a frequency distribution table of a bivariate data, means two variables. The variable is circumstance and gender. Notice both of these are qualitative variables, and we can actually do this for qualitative variables. Okay, so we have these, the way the table is given. And the questions that follow in part A, find probability of C1. C1, remember that means probability, the circumstances at work. Okay. That's the injury. The injury occurred at work. That's circumstance 1. So probability of injury at work, that's part A. Well, injury at work, let's see. The total, there were 9.3 total here, right? 9.3 out of 61.4. 9.3 divided by 61.4. Whatever that turns out to be. I'll put in the numbers in a moment here. Okay, so this probability is going to end up being about 15.15. 15, a little over 15%. In part B, find probability of C1 given S2. That means what is the probability that the injury occurred at work given it was a female? S1, S2 is female, right? Not S1 would be male. So C1 given S2 means given the selected individual is female, what is probability that the injury happened at work given it's female? So probability of C1 given S2 is going to be, now given S2 from the table, we only look at these folks. We only look at female group, which is 25.8. Okay, you see how that conditional probability again restricts the sample space to only those having the condition, in this case being female. What is probability of someone who was injured at work? That's going to be 1.3 divided by 25.8, and let's see, that's going to be about 0.0504. 0.0504, a little over again 5% probability of that. Now in part C, are events C1 and S2 independent? Okay, so a test for independent, remember, if the conditional probability of C1 given S2 equal probability of C1, that means gender has nothing to do with that. So this conditional probability is 0.0504, which does not equal to the marginal probability of just C1, which is 0.1515. So the answer is no. They are not independent. That means they are dependent. So what does that again mean? That they are dependent? That means whether the gender is male or female has a bearing on whether the injury occurred at work or not. So those are related. And in part D, is the event the injured person is male. The given person is male. Injured person is male. That's S1. Independent of event, the injured person was hurt at home. So here's home, here that. So we want to know probability of S1 given the person was hurt at home. Are those events independent? Okay, so let's see. We want to know if that's equal to the marginal probability of S1 regardless of the condition that's imposed on it, on that event S1. So probability of S1 given C2. Well, given C2, we're going to look at 21.4 in the denominator. S1 in that column, there's only 9.8 in that position of males whose injury occurred at home. And probability of selecting a male in the group is 35.6 out of 61.4. And these probabilities, they don't equal. So the answer again is no. So it seems like gender has something to do with the incidence of injuries either at work, home, and other. Means it's not uniform. That event is not uniform across gender. So there you have it. With that, again, a brief lecture at that for this section. So we are done with section 4.6, the multiplication rule, and we only have one more section after this. So this will wrap it up for this section.